Welcome to Decision Analysis for Agricultural Development. I'm Cory Whitney, and you've reached parts 5 and 6 of this mini series. In this part, I will talk about a few case studies related to, I've hinted at them actually already, but a few case studies related to decision analysis and how we apply it. And then I will give you a few conclusions. So that's part 5 and 6. I hope you enjoy. Please get in touch if you have any questions or issues. Go back and watch the first videos if you haven't yet. And I look forward to talking with you in the various channels that we have for our course. Now for the promised case studies and conclusions, part 5 and part 6 of the mini-series. Some case studies, we've worked on these with a number of organizations, ranging from Slow Food to different universities and ministries and CG centers around the world. And these two case studies that I'm going to talk about took place in East Africa and Kenya and in Uganda. Here we are in Uganda working on those tables that I talked about earlier in these roundtable workshops. We spoke of this before, so just briefly to remind you about Uganda's Vision 2040 and how we treated this as one decision context. So Vision 2040 calls for the industrialization of agriculture in Uganda, the movement from smallholder to industrial agriculture, with the idea that this will have an effect on the nutrient composition of people's diets, that it will decrease malnutrition. Yeah, and this is incorporated into NPA plans, the National Development Plan, and it's aimed at really addressing what Uganda's development goals in relation to the SDG 2, zero hunger. All of those goals are focused really, all of those policies are focused really on achieving this goal. And we said, okay, what is the effect? How will industrialization, urbanizing rural farmers and industrializing agricultural landscapes, what will that do for nutrition? What is that likely to do? So here's a tweet from the president, Museveni, and he wants essentially to follow Europe, really. Wants Uganda to follow the European pathway from rural agricultural population to an urban and industrialized agricultural population. So what are the implications, or questions really, what are the implications for human nutrition, and can this decision be improved at all? So we knew that the industrialized system would be comprised of mainly cassava, beans, bananas, rice, and potatoes as staples, with beans and export crops like tea and coffee. And we knew something of the traditional agricultural system, the structure of that system, which I'll talk about in a minute, because I spent a lot of time with farmers, and I knew we had a lot of farmers on board who could help us understand the composition of those farms, smallholder farms. So we created an impact pathway with nutrition as the outcome variable, that is the outcome of interest. And we said this will be comprised of nutritionally, so the intake of energy, vitamins, macronutrients, and micronutrients, which will necessarily come from yields, whatever is grown, those yields, which will be comprised of a normal yield with a yield increment, that is any increased yield through application of chemical fertilizers, etc., under the industrial system, and the food over the total food production area, which is the total farm area, any land equivalent, that is any additional productive area that may be achieved through something like agroforestry, and any non-food area, that is areas that are kept for example, houses, roads, and also for non-food production, like export-oriented coffee, etc. And that nutrition, the nutrition that people get from this food that's grown, will be subject to nutrient losses through possibly methods of cooking or overcooking, and also post-harvest losses, which are quite common. Food rotting before it's able to be consumed. And what we did was we could, as we talked about before, generate this conceptual understanding. This is a simplified version. Of course, these relationships are much more complex. But then in order to understand how these interact, we could say, okay, some of these have a positive or a negative influence, and what is the strength of this relationship? So we, in addition to that, instead, as we said before, of providing single values for these, we provide a distribution of uncertainty. So we do that for all of these, describe the relationship, positive, negative, perhaps more complex, and we describe a distribution. It can be a normal distribution, which you're seeing here, or it could be have any sort of form of heteroscedasticity or even be continuous. Regarding food production area, we had some data from the field. This is a typical farm, so the dimensions and composition, and also how much of the area is taken up for various crops. This is a standard, a sort of generic farm, standard smallholder farm today. And we can see here in the box plots from the Monte Carlo, we ran it 10,000 times, and you can see the distribution of outcomes. This roughly reflects the distributions from the inputs that we put into the model, of course. And we can see here that under Vision 2040, on the top graph of these box plots, the total production area is more. That is, more area is for production, right? There's no home, there's no road, there's no garden for relaxation, but just pure production, with much greater distribution of uncertainty on the side of the home gardens on the right-hand side here, the blue box plot, but lower total production area. Whereas the non-food production area, we can see the lower box plot here, is different because the non-food production area is still agricultural production, but much of it is export-oriented in the Vision 2040 system, whereas the home gardens are largely about food production, and the living space doesn't take up as much room as all of that non-food production does in the other system. In terms of yields in this model, we also ran this Monte Carlo to estimate the yields annually, and this is generic, so across both models, with an additional yield. That's the lower violin plot you're seeing here. So the additional yields from all the inputs, that is all the agrochemical inputs, in tons per hectare. So staples and pulses, they get some boost, right? From in the industrial scale system, they get some boost from these chemical inputs. Smallholder farmers generally don't have access to those. And in terms of nutrient contents of the foods that are coming out of these yields, we also generated this Monte Carlo model generated distributions for these, and we can see the the nutrient contents of these various types of crops: vegetables, staples, spice, pulses, and fruits. And you can see fruits have quite a bit of vitamin A, whereas staples and spices tend to have quite a bit more energy than the other products. And essentially what we did is to take those different distribution shapes that we generated for those models. We followed Doug Hubbard's work, some of our own research. We had data from there. We used databases, and we used some things from the National Planning Authority to generate these distributions. We run that in that model function we talked about, which selects, as we talked earlier, the Monte Carlo sort of selects randomly from this distribution, but it selects much more from the higher points of the distribution, and used a whole bunch of functions from the decision support package, and took from the results there, I take those 10,000 outputs. So we have 10,000 model runs. In red is the Vision 2040, and in blue is the home garden, the typical smallholder home garden system. And you can see that 96% of those 10,000 runs, vitamin A from the home gardens was superior to those in the Vision 2040 system, in the industrial scale system. So that means 96% of the time, the model selected randomly from all the distributions in our model and came up with an outcome that was better in terms of vitamin A in home gardens. And this is, we ran that also over the months of the year. So there are lean months, there are more difficult times in the year. And you can see here, these are 12 months. And those are micrograms retinol activity equivalents of vitamin A. So that's what the stuff you can use, really, the stuff that people can use for their body functions. And you can see that it's not in every case that the home gardens outperform the Vision 2040. There are times when Vision 2040 also does well. And I've put a line here to show the average requirement that we're expecting. So that's actually how much you would need. And most of the time, home gardens, that is smallholder farms, are able to produce enough, generally enough or just barely not enough vitamin A. So it's critical in both situations. But certainly under Vision 2040, with those production systems, it would not be sufficient for people to maintain vitamin A and to avoid vitamin A deficiency. And then we do something here, the value of information. Doug Hubbard calls this the cost of being wrong times the chance of being wrong. So here we have the value of information test on the variables within the model. And for energy, the total amount of energy and kilocalories per year, 81% of the time, Vision 2040 outperformed. That is, the industrial scale agricultural system outperformed the home gardens, with an important variable, something that we should measure in order to get more information, because 20% of the time, home gardens are still better. So is this really a clear decision? Not entirely, because there's a variable we might measure to find out more about this key knowledge gap. For vitamin A, no knowledge gap was identified. So for vitamin A, it's just clear, relatively clear. 96% of the time, home gardens are better at producing vitamin A. We do this for all of those nutrients that we talked about, and find that for some of them, there are variables that we could measure to understand more about this distribution and whether the decision is clear. So if we're basing our decision only on energy or only on carbohydrates, only on protein, then we should make some more measurements. But if it's on vitamin A, vitamin C, or beta carotene, we shouldn't really do that. There are large uncertainties, certainly. There's a lot of overlap, as you see, but the answer is still clear for most nutrients. And Vision 2040 is likely to reduce the production of many hidden hunger nutrients. These are nutrients that are not immediate causes of hunger, but they're causes of hidden hunger. That is, issues related to nutrition that are not immediately visible, like stunting and and thin people, things like this. So another example I'd like to talk to you about is the benefits of fruit trees. It's similar in some ways because it's also about nutrition and agricultural production. Kenya, as we talked about in an earlier video, actually in the introductory video, Kenya seeks better nutrition outcomes, and they've outlined this idea in several of their strategies and policies. They'd like to plant more fruit trees at the national level and local level, but there's a lack of scientific support to anticipate the specific policy outcomes. And again, we have this question about a link between production and nutrient gaps. And really, the development decision may be clear. We should provide fruit trees, but the nutrition outcome in the end may not be totally clear. So we're looking at this uncertainty and try to formulate some decision support for this effort, should there be an investment in fruit trees. So we generate, again, a conceptual model, something that represents our causal understanding. This is, again, a simplification, but essentially management will affect production, obviously. Production systems affect dietary intake, that is, how much is growing, how well is it growing, will affect the available food for dietary intake. And the household will affect management and dietary intake, that is, how do they manage their farm and how do they cook their food, what kinds of food do they like to eat. And this dietary intake will be a major factor in determining the nutrient gap, that is, whether or not people have a lack of any of these things: energy, iron, vitamin A, and zinc. You saw these people before. They're getting calibrated, and these are nutritionists, farmers, local experts, development researchers, and they're trained to assess their uncertainty, to provide distributions of uncertainty. In this case, actually, to provide quantitative understandings in the form of conditional probability tables. And what we do is we model the production and the management and see how that influences the dietary intake and the ultimate gaps. You saw this earlier. Here it is stretched out in a little bit bigger form. Maybe you can actually see it. But here's that zinc gap per person, given that trees have been planted. And in this Bayesian network, the nodes, those little circles in the graph, are called the parents. If they have any below them, those are called a child. So makes sense. There's like a family tree here. Zinc has lots and lots of parents and grandparents, and the states of those variables influence the condition of zinc gap per person. That is, how many people, and there are all kinds of factors, of course, that go into this. The key findings from these model results is that fruit trees can provide many benefits. Here, again, lots of uncertainty and a huge amount of overlap, right? But we can see there's a nutrient gap. That is, how much is lacking in people's diets. And when the trees are planted, there's slightly less gap than when there are no trees. Vitamin A, again, slightly less of a gap when trees are planted. The same for zinc. And for energy, there's so much overlap that we probably can't be very clear on this. But here's the line to represent, again, the estimated annual nutritional needs. And we're seeing here what's a sufficient diet on the left and what's not a sufficient diet on the right. So obviously, regardless of whether these trees are, generally, regardless of whether these trees are introduced, there's still going to be nutritional issues. Trees are not the silver bullet to deal with nutritional issues on smallholder farms. There are various interacting factors that influence fruit tree planting and subsequent nutrition outcomes for farmer households in Kenya. And decision analysis can provide appropriate support for understanding the probable outcomes of nutrition-related policy decisions. Those are our main conclusions. And now conclusions for the overall work. The decision sciences or decision analysis tools and methodologies can offer a fitting paradigm for agricultural modeling. They're geared towards solving problems. They don't aim at precision or at these ultimate answers, but at offering comprehensive advice. And if solving problems and supporting decisions, facilitating development in complex systems is our goal, we should adopt decision analysis thinking as our research paradigm. So thanks very much for sticking through the 6-part series. And I'd like to congratulate you on making it through some rather difficult material. And I'd welcome you now to look back at the models that you've developed and think about how these might be applied for decision support. And I welcome you to contact us if you have any interest in applying this in your own research, or if you have any feedback, critique, or constructive ideas about how you think this might be improved. I look forward to hearing about your modeling approaches and talking with you in the various channels.